We're going to have two talks in this paper, in this session. The first talk is going to be about a paper that's called Algebraic Linear Analysis for Number Theoretic Transform in Lattice-Based Cryptography, and the talk is going to be given by Mingchen Tsai.
Thank you. Okay. So this is a joint work with Junming, Jiaxiang, and Xiaomu, Boya, and Boyin. So last year, NIST has published 3 post-quantum standards. And following these standards, the implementations may still be optimized for better performance, but also become error-prone. Since bugs in software implementations can lead to catastrophic vulnerabilities, so it's important to verify whether the implementation is correct or not. And in this paper, we focus on using formal verification techniques to verify the functional correctness of implementations. And in particular, we focus on range properties. So security properties such as side channel resistance is not handled in this paper. So there are already many solutions for verifying cryptography code that guarantee range properties. But we found that most of the solutions rely on satisfiability modular series solvers. And only few of them involve non-Montgomery Marmos or 32-bit arithmetics. In our own experimentation, we found that it is difficult for SMT solvers to handle highly nonlinear 32-bit operations and reason about ranges at the same time. So for 16-bit Barrett Marmos, SMT solvers works pretty well, but for 32-bit Barrett Marmos, it's very difficult for SMT solvers. So to verify 32-bit and arithmetic and also non-Montgomery Marmos more efficiently, we introduce an adaptation of the ISL library into the cryptoline verification toolkit. The ISL library handles ranges arising from linear arithmetic relations extremely well. And with ISL, we can verify both Blanchard and the Barrett multiplication easily. And we can also extend this to 32-bit arithmetic effortlessly. So with ISL library support in cryptoline, we verified the highly optimized MLCAM and MLDSA NTT implementations, including 3 newly verified results. The MLDSA implementations on AVS2 and ARC64. Also, MLCAM Planta-based implementations on Cortex-M4. So what is the ISL library? It's an open-sourced C library for manipulating relations over exact integers bounded by linear constraints. And it supports all standard set operations such as intersection, union, emptiness check, and projection. And this library has been used for program analysis such as loop optimization in GCC and LLVM. So here I show you 2 examples that can be represented by the ISO library. So it can represent even integers between 0 and 100 by the following formula. It can also represent a set of integers I between 0 and n such that I mod 10 is smaller than or equal to 6. And this slide shows you the one-level NTT, but I will not go into the details. So basically, NTT computes isomorphisms between question rings. And this is done by applying different butterflies and at one level of entity. For example, the colleague-to-kid butterfly and the gentleman sand butterfly. And in each butterfly, there are some field operations involved, like multiplication, addition, and subtraction. And to compute field multiplication efficiently, various reduction approaches are used, such as Montgomery reduction, Barrett, and Prandtl reductions. So we want to verify entity implementations. And to verify entity implementations, we want to specify its correctness specification as a whole triple. And this whole triple means that starting from a state S, satisfying the precondition phi, if the program terminates at final state T, then T must satisfy the post-condition psi. So for the verified entity implementations, we specify the isomorphisms between the input and output polynomials as the post-conditions, as well as some coefficient ranges that are crucial to program correctness. So now we have specified the entity implementations, and we can use script line to verify those specifications. And script line applies two verification techniques to verify a whole triple. The first one is SMTQ-PV, is used for bit accurate analysis, such as range checking. The second one is algebraic abstraction, and it is used for the analysis of nonlinear computation. In algebraic abstraction, a program is first reduced to a system of polynomial equations, such that a program trace corresponds to a solution of the system of polynomial equations. So for example, consider the SPL instruction, which split a 32-bit vector T into two 16-bit vectors, TT and TB. And the corresponding polynomial equation for this instruction is 2 to the 16 multiplied TT plus TB equals T. And I think it's easy to see that a program execution of the instruction will correspond to a solution of the corresponding polynomial equation. But such algebraic abstraction is only sound under a sense of overflow. So for example, consider the add instruction. The corresponding polynomial equation is R equals A plus B. So obviously, if A plus B overflows, then the program trace will not be a solution of these polynomial equations. Although the algebra abstraction in Crypt9 works pretty well for proving nonlinear computation, it has some limitations. The first one is that it supports only equalities and modular equalities. So we cannot use algebraic abstraction to prove range, to do range checking. And the other limitation is that it allows spurious solutions not corresponding to program traces. So consider the SPL instruction again. There is one possible solution for this instruction, which is TT equals 0 and TB equals T. So if the big vector T, the high 16-bit of T, is not all 0, then this solution would be a spurious solution that does not correspond to a program trace. So a simple way to address this problem is to remove spurious solutions by adding more linear constraints, which bounds the ranges of TT and TB. And so with the two additional linear constraints, it makes the solution to the linear equation unique, and also remove the spurious solutions. Such linear constraints can be solved by polytope libraries with exact integers. So for example, the SMT-LI solvers, PPL, and ISL. We actually tried all the three polytope libraries in our experiments, and we found that ISL is the best in our experiment. So we called our new technique algebraic linear analysis, which allows both equalities and inequalities in linear constraints. But since there are still integer polynomial equations, so this analysis is sound under the absence of overflow, same as the algebraic abstraction. Consider the reduction to linear integer constraints. There are some trivial translations to the constraints, such as the addition instruction. But there are still some non-trivial translations. For example, the conditional move instruction. So this instruction assigns A to R if C is true. Otherwise, it assigns B to R. And we translate this instruction to 4 linear constraints, which bounds the ranges of R minus A and R minus B, depending on the value of the condition C. So for example, consider this R minus A. If C is true, then R minus A must be 0, according to these two constraints. But if the condition C is 0, then R minus C is in a very big range, which is safe, because the difference is always in this range. So there are also some other non-trivial translations. So now our algebraic linear analysis supposes both equalities and inequalities. So it can reason some variable ranges. And since in the soundness checking, we want to check if there is an overflow. And this can be done by range check. So actually, we can apply our algebraic linear analysis to detect overflow. But as I said, the algebraic linear analysis requires the absence of overflow. So this is some kind of circular reasoning. But by induction, we can prove that this approach does work. So we call this technique algebraic soundness checking. And during the verification, Cryptide offers cut instructions to allow the verifier to split the verification of a large program into smaller or triples. But it happens that for here, we have 2 post conditions to be verified. And the 2 post conditions requires different ways to split, to decompose the program. So the first one requires a decompose between P1 and P2. And the second post condition requires a decomposition between P0 and P1. So currently in the crypt9, you can insert cut instructions after P0 and after P1 and result in the 3 smaller whole triples. But the problem is that here, we want to verify the conjunction of the post conditions with the precondition rho 0. But the problem is that rho 0 is used for proving psi 0, not psi 1. So it may contain not enough information to allow us to verify that psi 1 is correct. So here we can actually obtain a better decomposition such that both psi 0 and psi 1 can be verified. So we developed a multi-track verification in crypt9 to obtain such a better decomposition. So basically, we say that these are on the track 1 and these are on track 2. So they will be decomposed separately. In the benchmarks, we verify MLDSA implementations in PQC on AVS2 and ARC64. We also verified several MLCAN implementations with Montgomery, Barrett, Planck, and also Planck multiplications. And this slide shows that with ISL, ISL is the best in verifying those entity and inverse entity implementations. And the SMT QFBV works well for 16-bit implementations of MLCAN, but still ISO is the best. And also SMT QFBV does not work well for MLDSA, 32-bit implementations of NTT. For SMT LIA servers, it works pretty well for the PQC AVS2 inverse NTT implementations of MLCAN. And for other cases, it just time out and does not behave good. So to conclude, optimized entity implementations have become a critical component in lattice-based cryptography. There are various entity, like incomplete entity, twisted entity, and maybe entity with good streak. They are implemented on various architectures, such as AVX2, ARC64, Cortex-M4, and so on. And they have different multiplication reductions implemented, such as Montgomery, Barrett, and Planck multiplications. So for such entity implementations, the correctness verification, we think algebra linear analysis is our answer to verify such diverse entity implementations. Compared with SMT QFBV, our algebra linear analysis is more scalable. And compared with algebra abstraction, our analysis support inequalities. So we also report 3 new verification results. And if you are interested in the ISL implementation in crypt9, here is the URL. And we also have an artifact, but I don't provide the URL here. You may find the artifact on the CHES website. And thank you for listening.
Thank you very much for your talk. We have plenty of time for questions. Please walk up to the microphone if you have any questions. Let me start with one. So the main focus of this work was lattice-based cryptography. Do your techniques also help with verifying other crypto systems, something like elliptic curve cryptography, or is it really very specific to entities and MLChem and MLDSA?
Yeah, we are trying to see if this techniques also works for other crypto schemes. So for example, HQC and maybe other schemes. But as the name, algebra linear analysis indicates, so only linear computations are supported. So if some operations is unlinear, then it won't help. Yeah.
Thank you. Any more questions? Seems like there's no more questions, so let's thank the speaker again. Right, let's move to the second talk of this session. Can we get the slides for those, please? So the second paper is called Tailorable Codes for Lattice-Based Chems with Applications to Compact MLChem Instantiations, and the talk is going to be given by Thales Paiva.
Thanks, Matthias, and thanks for coming, everyone. Okay, let me just get this. Okay, thank you. Okay, let's jump straight into it. The idea for this project initially was to think about how to compress MLChem. And it seems like an easy thing to do. You just use fewer bits for the public key and for ciphertext. But, and this is effectively what Kyber does or what MLChem does. But the problem is that you reach, so the problem is that the decryption failure rate stops being negligible pretty quick when you start getting rid of some bits. So you have to do something smarter. Initially, we started using some parameter exploration and trying to use some existing error correction codes, such as binary codes or lattice codes, and they actually work. Like we were able to see some improvements on the overall Kyber or MLChem size, but that required changing core parameters. So after doing the parameter exploration, we ended up needing a different modulo Q and a different polynomial degree n, for example, or something like that. So different Qs to allow for more errors to be corrected with larger Qs, for example, and we had to increase the degree n to allow for a binary, so for the expansion of a binary code. And this is not a very good idea because this can break the NTT compatibility and also the compatibility with other optimizations. Furthermore, we also needed to add additional assumptions, such as the independence among noise coefficients, which is known to be problematic when combining lattice codes, lattice-based schemes and binary codes. So our approach ended up being to devise a new error correction code, very suitable for lattice schemes, and that come with a very detailed DFR analysis, so that we don't need to use independence among or independence assumptions on the noise coefficients. And it allowed us to get up to 8% compression in MLChem ciphertext or public keys with a minor performance impact. And we can even support parameters with better performance. Okay, so let's start seeing how error correction appears in lattice-based chems, because in MLChem it appears in a way that it's disguised as a decoding mechanism. So all lattice chems based on LWE or learning with errors or learning with rounding, they face the same challenge. So keygen adds noise to hide the secret key, and the encryption adds noise to hide the message. But during decryption, you will combine the secret key with the ciphertext, which ends up accumulating the noise from both keygen and encryption. So you have to use an error correction to recover the correct message, because during decryption you see just a noisy version of the message that needs to be, you need to reduce the error or to remove the error from it. Therefore, the quality of the error correction that you use here is very important, because you need a negligible decryption failure rate, or DFR, to ensure security. Otherwise, you can do some reaction attacks or decryption failure attacks, which are well known to be very dangerous to code-based and lattice-based schemes. And also using better codes means you can drop some least significant bits, which will give you compression, which is the main focus of my work. So let's briefly look at the nature of the error to be corrected in MLChem. I won't cover MLChem, which is here just as a side note. But what you need to do is, what you need to know is that in MLChem, the decryption is successful when the polynomial delta m, which is the noise polynomial that is added to the message, or that you see in the message during the decryption, has small coefficients. And this is how this polynomial delta m is defined. It's defined as a product of two vectors of small polynomials, another product of vectors of small polynomials, and then a small polynomial, and then there is this delta v, which comes from the error from the lossy compression and decompression. So these two factors, the delta u and delta v, that comes from the compression and decompression, these are small but are uniform, and all other components come from the centered binomial distributions. So they're distributed like a bell-shaped distribution. So therefore, the coefficients of delta m are sums of somewhat Gaussian or bell-shaped values, or values that follow a bell-shaped distribution, and uniform components. So this is the nature of the noise that we need to correct. And one thing that it's important, consequence of how the delta m is defined, is that the coefficients of delta m are not independent. Because these vectors of polynomials here that you combine with a dot product, you have to consider that there are polynomial multiplications inside it that will make correlation appear between coefficients of the delta m polynomial. So that's why we cannot assume independence of them. Okay, so the typical way in which lattice chems deal with this type of error is to encode 0 as 0 and 1 as q over 2, the modulo over 2. This is done by most of the lattice-based schemes, and it's very simple and effective. So it's easy to implement the encoding and the decoding. So for decoding, you just see if your number, modulo q, is closer to 0 or closer to q over 2, and you decode to 0 or 1 correspondingly. This also allows you, or allows MLChem, to have a simple DFR analysis using the union bound that doesn't require any independence assumptions on the coefficients of delta m, which is great. However, this is somewhat suboptimal because there are denser codes for correcting bell-shaped errors. So in this figure here, we can see the MLChem's code in 2D. And these circles represent the radius of the coding radius that you get. And assuming a bell-shaped distribution whose curve lines are somewhat circular, or actually circular, you can see that there are these gaps here that are kind of annoying. Like you could do better for decoding these bell-shaped distributions. And one alternative would be to use a lattice code, for example, which encodes, which packs the space much more densely. However, the lattice codes are somewhat problematic because if you're using MLChem, it's important for example, if you start on 0, if you sum q, which is 0 modulo q, you want to get back to 0, and this doesn't happen here. You get to this annoying point that doesn't mean anything. Different than Kyber's code, where if you sum q, you get to 0, 0. If you sum q again, you get to 0, 0. Right? So lattice codes cannot be directly applied to most lattice schemes because for you to be able to fit a lattice, or for the point of your lattice to meet the hypercube ZQN, you need a very specific values of q. For example, powers of 2, which is the case of New Hope. So the existing approaches that we have for error correction in lattices are, apart from the 0 to 1 and 0 to 0 and 1 to q over 2 simple encoding, is to use binary codes, which are very fast but problematic. So this is the case for LAC, which used BCH codes for message bits, which is very easy to implement and well understood, and maybe not so easy sometimes in constant time. But they require independent assumptions on the noise coefficients. And these often leads to very optimistic DFR analysis, which are known to cause issues. So they, in like analysis, it was shown that that LAC underestimated by a lot the DFR, which ended up being a severe problem for the scheme. And another problem is that they require a larger n to accommodate extra coefficients. So you will need to change a core parameter if you want to support the binary encoding. So the other approach, which I described in the last slide, is to use lattice codes, which are denser but somewhat inefficient. Also, the decoding is much more difficult than, or less natural than for BCH codes or other efficient binary codes. So this is the case for New Hope in its first version. So New Hope first used lattice codes, but they then replaced it with repetition codes because it was much easier to implement and to explain. So these codes are good for correcting bell-shaped noise, but can be bad if your noise is not shaped like a Gaussian distribution. They are not so easy to implement efficiently, and the main problem is that they restrict your modulus Q, which can impact the use of NTT. Okay, so our solution is then to combine lattice codes, like the good part of lattice codes, enforcing some structure so that we can repeat, or so that the code is periodic, or so that it preserves the structure of the hypercube ZQN. So we call this code MINO because it's not a lattice code, and it can be defined for any dimension mu, as this set here. So you take a G, a matrix G, an integer matrix G, that is a circulant matrix generated by this sparse first row. So you just get this row and repeat it using circular shifts. The first coefficient is Q over 2, and the other one is beta, which is a scheme parameter. So beta is called the tailoring parameter, and we will see why it's called like that in the next slide. And then we say that C encodes a mu-bit message M when C is equal to G times M plus multiples of Q in each coordinate. So this, by constructing the code as this, we enforce that the structure is preserved modulo ZQN. So we have something like the lattice code inside the core, but because of this construction, we get the 0, 0 to the right position, right? So it's a pretty simple construction. We just get the core of the lattice code, and we repeat that in each hypercube. So what we guarantee by that, so what we get by that, is that no condition on Q needs to be enforced. So this can readily be integrated into MLChem, Sabre, and New Hope. Now, so remember that the error to be corrected, which are the coefficients of delta M, are sums of somewhat Gaussian and uniform values, right? But the strength of the combination will define the overall shape of the distribution. So if it's if it's dominated by the Gaussian part, it will look like the curved lines will be circles. If it's dominated by the uniform part, it will be a more square distribution. So one core observation, and actually a motivation for defining the codes as we did, is that these codes can be tailored to specific error distributions using beta, right? So we can build codes that are very effective for decoding errors that are particular to each scheme or each scheme parameters. So the intuition behind how we do that, so we do that with using a bunch of heuristics, but you don't need to worry because the DFR is then bounded without any assumptions. So we just do some weird assumptions for tailoring, but then it doesn't affect the scheme's security. So the intuition is that we model the noise distribution as squircles or squared circles, which are circles in the p-norm, so that we can capture the amount of part that is a circle and or circular or Gaussian, and the amount of the noise that is square. So in MLChem, the parameter that is mostly responsible for the overall shape of the distribution is dV, which is the number of bits used for compressing coefficients of V. And you can see how dV affects the parameters here. So if you drop all bits of V, then you get a very square distribution. Like these are the curved lines of the distribution. And if you use a high value of dV, then it's pretty much circular. Like the Gaussian part dominates. So now, if you want to tailor the code or to find the best code, what you do is you pack the squircles. You find the best packing, the best mood-dimensional packing of these squircles. And you do something like this. You determine the p-norm where the level curves of the error distribution are somewhat circular. So this will capture. This will capture essentially this overall shape. And once you find P, you need to find the value of beta that maximizes the minimum distance of the middle code in the p-norm. So this is the squircle packing part. And an important remark is that you know that packing is usually a very hard problem, but we are not doing a real packing here. We are doing packing with the minor code. So having only one tailoring parameter is what makes this step efficient, right? You just need to find beta, which we can do using ternary research, which is what we describe in the paper. And our Python implementation, which is not very efficient, performs tailoring for dimensions up to 8D. Could do more, we could implement it in C, we could do something smarter, but it was fine for the cases that we are interested. So here you can see the packing happening. So if your distribution is more squared, then beta is smaller, and you get a code that is closest to Kyber's or MLChem's original code. If you get rounded or very circular shapes, then you get close to the lattice code inside, but you can do some things in the middle, which is a quite interesting thing. And this has some interesting theoretical contributions, because I never saw that happening in coding theory, where you use this type of modeling for the error. Okay, so how to bound the DFR? So once the code is tailored, we can compute the DFR. So compute an upper bound on the decryption failure rate. And for that, we extend the analysis of the original New Hope. However, the minor codes require convolutions of very large distributions in arbitrary precision, which is not the case for New Hope, because their lattice code is very simple and you can do a bunch of optimizations. So we were only able to do the analysis for 4D codes. We are not able to go to 8-dimensional codes because of some hardware limitations and some analysis limitations, but we believe that it might be possible to go for 8D. And this is the overall, it's a very mathematical type of algorithm optimization. So you just, you need to see the probability that every 2 pairs of neighbors, when you start in one neighbor, you want to compute the probability that you start in one of the neighbors and gets add some noise to it and gets back to the wrong neighbor. You compute this distribution and you do an union bound over all these possibilities, and you can do the analysis. But the hard part is this one here, because we don't want to use any independence assumptions, so we need to compute implicitly a very large joint distribution for the coefficients that we are using for the code. So what we can do with that? So here is a comparison between the ciphertext sizes and DFRs. So we set some DFR targets to give some flexibility based on the DFR levels achieved by MLChem and Sabre, or actually the DFR levels that Kyber also achieved historically. So we did some, we defined the DFR to give us some freedom, but not too much freedom, right? So we didn't want to do some unfair comparison. So what we can see here, so this indicates, like these double circles indicates the real MLChem parameters. So what we can see here is that the DFR, when we use the 4D codes, like it's much, much smaller. However, in this case here, we don't care, because Kyber is already, like, it's already too small, so we don't need to use it doesn't make sense to use a more complex code here. However, what we see is that there are parameters offering much more compression, that for which we can cross the threshold of the DFR. So we can make some other points to be viable solutions. So once you define the DFR target, using better codes can help you pass this threshold. But there is a problem, right? The coding is much worse, essentially. So for the performance, the encoding is very efficient because of the sparse generator. So our encoding mechanism is designed to be very fast for encoding because we are using a sparse cyclic matrix. However, for decoding, it's a bit more complicated. So we are able to exploit the cyclicity and sparsity for decoding. I won't show the algorithm here, but everything is implemented in constant time, and it's an artifact, and it's available on GitHub. We provide an efficient decoding for 2D codes by noticing some symmetry, so it's exceptionally fast for 2D codes. But for arbitrary dimension, our decoding performance degrades exponentially because we need to track every possible code word inside the main representative square or hypercube. However, it is very practical. So up to 9D, it's more efficient than HQC decoding. So we are in a reasonable range for decoding complex codes. So for the performance numbers are as follows. So we consider MLChem's full decoding, which is the function poly-to-message, on Cortex M4. And we have 2.6 longer time for 2D minor codes and 5.6 longer time than for using 4D minor codes, which is a bit crazy, right? In every section here, you see some guys talking about 2.6 or 5.6 speedups, but we have a much worse performance. But these are not really bad numbers because the coding is not MLChem's bottleneck, right? The full decapsulation takes orders of magnitude more time. So here are the results for the compression that we get using the big picture. So we are allowing us to change the parameters for compression, which are the UDV, of course, because we want to compress ciphertexts. And we also change eta 2, which is the centered, we allow us to change the centered binomial distribution parameter. And why is this allowed? Just a brief comment. We allow that because the security of MLChem 512 is based on both LWE and LWR. So we allow us to use the LWR for levels 1 and 3, just to get some flexibility. And what ends up happening is that because we are able to reduce so much the number of bits required for MLChem, then LWR, or the learning rate rounding, begins taking effect, and we are able to even go to use eta 2 equals to 0 with a negligible DFR, right? And because we are using eta 2 equals to 0, we not only get compression for levels 1 and 3, we also see some speed up. Because now during the re-encryption, you are not doing some resampling of E2. But for level 5, we didn't mess with this parameter, and we get up to 8% compression using 4D minor codes with a minor impact on performance. So for public key compression, we consider public key compression because it was used in the first version of Kyber. It's not used anymore, but can be useful for some applications. And for that, we didn't change any compression parameters for ciphertext. We only compressed the 12-bit coefficients in the public key to 11 bits. And the DFR stayed virtually the same as MLChem without compression. So we kind of get these compression numbers for public key for free, without any impact on the DFR, but with some impact on the decaps. So the poly-to-message, the decoding algorithm, it takes a constant amount of time. It doesn't scale with the security level. So in level 5, we have a very minor impact, but in level 1, we have some impact, right? Okay, so for future work, one thing to consider is how to improve the decoding algorithm, which is the main problem. If we want to go to 8D or to higher dimensions, we need to do a better decoding algorithm because the exponential part is not very attractive. And for that, we can maybe exploit symmetries like the ones that are used in 2D decoding. I think that there are some symmetries. I found them, but it's very difficult to exploit them. But I'm confident that with someone smarter than me in that part can possibly have some ideas. So yeah, so using a better decoding algorithm can help us achieve decoding in 8D or maybe even higher dimensions in MLChem or other lattice-based schemes. And there might also be some implementation aspects to be improved because we did a constant time implementation, mostly in C. Didn't do some assembly optimization, didn't do too much optimizations using vector instructions. But there might be some interesting things to be explored in the implementation direction. And the other part is on the analysis of the DFR. So the question is how to compute the DFR in dimensions larger than 8D for MLChem or other schemes. So MLChem parameters make it difficult to bound the DFR beyond 4D, but there might be some other schemes where we can actually compute the 8-dimensional distribution. Right? It is something particular to Kyber or to MLChem that has a lot of parameters or lots of margin that makes the DFR estimation very complicated. And maybe we can consider looser upper bounds or even symmetries to make this analysis work. And the final and actually most concrete or concretely implementable future work is how much these codes, or study how much these codes improve other lattice-based schemes such as Sabre and New Hope. So that's it for me. Any questions?
Thank you for the talk. We have maybe time for one question. Someone has a question? No questions. Okay, let me ask one very quick question. Can you comment on how these tricks may affect side channel countermeasures, constant time, and power side channels?
Thanks, Matthias. Thanks for the question. Yeah, so these tricks, so even though we implemented it in constant time, following constant time practices, like I didn't check really the assembly generated, it's just some implementation. The implementation is more complex, and I think, for example, if you're trying to mask that, it won't be as nice. Yeah, so I think we cannot sell that that it's very convenient for masking and for other countermeasures. We have to. I think this is more useful when you're talking about applications where you really need compression, but. Yeah, it is harder. Not as hard as HQC though. Like it's strictly easier than HQC and strictly harder.
Okay, thank you very much. So let's thank both speakers of this session again.